A tiny magnet can overpower the gravitational pull of our entire planet. Gravity is the weakest force in the universe by an almost unimaginable margin, 10 to the power of 36 times feebler than electromagnetism. This is not a minor detail. It is the greatest unsolved puzzle in physics, and its solution could shatter our understanding of reality itself. By the end of this journey, you will see how this glaring weakness might be our most important clue to discovering hidden dimensions folded into the fabric of space. What if our universe is just a slice of something far larger, and gravity is quietly leaking into realms we cannot see? How could the faintest force be pointing to the grandest truth? What does it mean for our place in the cosmos if most of existence is hidden from view? To understand why gravity's feebleness is so shocking, we need to meet the other players on the cosmic stage. Think of the universe as governed by four fundamental forces, each with a distinct and powerful role. The strongest of them all is the strong nuclear force. It acts like a cosmic superglue, holding the very cores of atoms together against unimaginable pressures. Without this force, protons would repel each other, and matter as we know it would simply cease to exist. It operates on a scale smaller than an atom, yet its power is absolute within its tiny domain. Then there is electromagnetism. This is the force we interact with every single day. It is the artist of the cosmos, responsible for all of chemistry, for light, for the very structure of molecules. It binds electrons to atoms, allows your nerves to send signals, and creates the dazzling beauty of a sunset. It is immensely powerful, trillions upon trillions of times stronger than gravity, which is why a simple refrigerator magnet can effortlessly defy the gravitational pull of our entire planet. A more subtle character is the weak nuclear force. This force is the alchemist responsible for processes like radioactive decay. It is what allows one type of subatomic particle to transform into another, a key process that powers the sun and makes life possible. While it is called weak, it is still staggeringly more potent than gravity. And then there is gravity. In this cosmic hierarchy, gravity is the ghost. It shapes the grandest structures in existence: galaxies, clusters, the very expansion of the cosmos, yet on the smallest scales. Its voice is barely a whisper. The numbers are almost impossible to grasp. Electromagnetism is 10 to the power of 36 times stronger. That is a 1 followed by 36 zeros. To put that in perspective, if the strength of electromagnetism were the distance from Earth to the Sun, the strength of gravity would be less than the width of a single atom. This is not a minor quirk. As renowned physicist Brian Greene has emphasized, this staggering disparity is perhaps the greatest mystery in all of physics. Our current theory of particles, the incredibly successful Standard Model, beautifully explains the other three forces, but gravity stands apart, an outlier that refuses to fit into the same elegant framework. This hierarchy is a glaring question mark on our map of reality. It tells us that something profound is missing from our story, that the answer will require us to look beyond the three dimensions we perceive. The weakness of gravity is not a bug in the universe's code. It is a clue, a faint signal pointing toward a reality far stranger than we ever imagined. This profound mismatch in strength forces us to ask an even deeper question. Why does gravity feel so different from everything else? The other three forces have found a comfortable home within a powerful theory called quantum field theory. In this framework, forces are not just abstract fields. They are carried by tiny messenger particles. Electromagnetism is carried by particles of light, photons. The strong nuclear force is transmitted by gluons. These particles are like cosmic postal workers, constantly exchanging messages that tell matter how to behave. This quantum picture is spectacularly successful, predicting the behavior of particles with incredible precision. But gravity, as described by Einstein's theory of general relativity, is a story of geometry. It tells us that gravity is not a force in the traditional sense, but rather the curvature of spacetime itself. A planet orbits a star not because it is being pulled by a force, but because it is following the curved geometry of space created by the star's mass. These are two completely different languages. One speaks in the discrete packets of quantum particles. The other speaks in the smooth, continuous fabric of spacetime. For nearly a century, physicists have struggled to translate between them. They have searched for a hypothetical quantum particle for gravity, called the graviton. Finding it would be the key to fitting gravity into the same elegant box as the other forces. Yet every attempt has failed. The mathematics simply breaks down. It is the ultimate case of trying to fit a square peg into a round hole. The equations that work perfectly for the quantum world produce nonsensical, infinite answers when applied to gravity. This is not a minor technical hurdle. It is a screaming sign that our understanding is incomplete. Gravity refuses to play by the quantum rules that govern every other part of reality. This profound disconnect suggests something radical. Perhaps gravity is not failing to fit into our model. Perhaps our model is too small to contain it. What if gravity's unique nature and its puzzling weakness are clues that it is interacting with a broader stage? This line of thinking does not see the struggle as a dead end, but as a doorway. The very fact that gravity stands apart, that it operates on the principle of geometry rather than particle exchange, points toward a breathtaking possibility. Its true nature may only be fully revealed on a larger canvas, in the hidden dimensions that could lie just beyond our perception. This staggering difference in strength is not just a curious fact. It is physics' most urgent and persistent puzzle, known formally as the hierarchy problem. Think of it this way. If the immense strength of electromagnetism were represented by the towering height of Mount Everest, then the strength of gravity would be equivalent to a single grain of sand resting at its base. The question is not just why this gap exists, but why it is so incredibly, outrageously vast. In our current equations, this gap is not stable. It is as if you stacked that grain of sand on a needle's point and expected it to stay perfectly balanced for billions of years. The slightest theoretical nudge should topple the entire arrangement, yet our universe displays this precise, fragile hierarchy with perfect stability. This tells physicists that something fundamental must be actively protecting this balance, something our models do not yet include. Nobel laureate Frank Wilczek has often highlighted this problem as a direct signpost to new physics, a clear indication that our current theories are missing a crucial piece of the cosmic puzzle. The hierarchy problem is a beacon. It shines a light on the incompleteness of our understanding and demands a revolutionary explanation. What could possibly account for such an extreme and stable difference between the forces? One compelling answer emerging from the frontiers of theoretical physics is that gravity may not be weak at all. Instead, its strength could be diluted because it is not confined to our familiar three dimensions of space. Imagine a drop of ink falling onto a thin sheet of paper. On the two-dimensional surface of that paper, the ink creates a small, concentrated stain. But if that paper is actually a slice through a much thicker block of sponge, the ink would seep into the hidden depth, spreading out and becoming far fainter on any single surface. In this view, gravity's apparent feebleness in our world is not its true nature. It is a consequence of its freedom to travel into extra, compact dimensions of space that are curled up and hidden from our perception. The hierarchy problem, then, transforms from a frustrating inconsistency into a potential clue. That incredible, unexplained gap between the forces could be the architectural signature of a larger, multidimensional reality, a hidden geometry that stabilizes our entire universe. The idea that our universe might have hidden dimensions did not emerge from supercomputers or particle colliders. It was born from a simple, elegant act of mathematical courage in the early 20th century. In 1919, a German mathematician named Theodor Kaluza wrote a letter to Albert Einstein that would quietly change everything. Kaluza took Einstein's groundbreaking equations of general relativity, which described gravity as the curvature of four-dimensional spacetime, and did something astonishingly simple. He added just one more dimension. He rewrote the equations for a universe with 5 dimensions, not 4. When he solved them, something magical happened. The mathematics did not just describe gravity. It naturally produced a second set of equations that perfectly described James Clerk Maxwell's theory of electromagnetism. In one breathtaking stroke, Kaluza had shown that by expanding the geometry of reality, the two great forces of the cosmos, gravity and light, could emerge from a single, unified source. It was a vision of profound elegance. Einstein himself was captivated, calling the idea thoroughly original. But a glaring question remained. If there is a 5th dimension, where is it? Why can we not see it or move through it? This is where Swedish physicist Oskar Klein entered the story a few years later. Klein proposed a beautifully simple answer. The extra dimension is not absent. It is simply curled up into an unimaginably tiny circle, a loop so small that it is far beyond any instrument we could ever build to detect. He called this idea compactification. Imagine a garden hose stretching across a vast field. From a distance, it looks like a simple one-dimensional line. But if you could shrink yourself down to the size of an ant and crawl onto its surface, you would discover it has a second dimension, a circular dimension wrapped tightly around its circumference. We, like the distant observer, only perceive the long, open dimension. The compact, circular one remains hidden from our coarse perception. Kaluza and Klein suggested our entire universe could be like that hose. We experience the 3 large, expansive dimensions of length, width, and height. But there could be additional spatial dimensions, curled up at every single point in space, at a scale a billion times smaller than an atomic nucleus. Their work was met with a mixture of awe and deep skepticism. It seemed like a beautiful mathematical trick, a theoretical curiosity with no connection to the real world. Yet they had planted a seed of monumental importance. They provided the first concrete framework, suggesting that the fundamental forces we observe might be shaped and separated by the hidden geometry of space itself. Their bold vision laid the conceptual groundwork for a question that would haunt physics for the next century. If gravity can feel the full geometry of these extra dimensions, while other forces are trapped on our 3-dimensional slice, could that explain why it appears so uniquely feeble in our world? For decades, the Kaluza-Klein idea remained a beautiful but isolated mathematical island. Then, in the late 1960s, a new and far more ambitious framework began to take shape, one that would not just accommodate extra dimensions but fundamentally require them. This is string theory. Its core premise is deceptively simple, yet its implications are universe-shattering. What if the most basic building blocks of nature, the electrons and quarks we call fundamental particles, are not zero-dimensional points? What if they are instead unimaginably tiny, one-dimensional loops or strands, vibrating like the strings of a cosmic violin? This single shift in perspective changes everything. Just as a single violin string can vibrate in different modes to produce a rich spectrum of notes, a low C, a high G, a resonant A single fundamental string can vibrate in different, incredibly complex patterns. One specific vibrational mode might manifest as an electron, another distinct pattern might be a quark, yet another, profoundly different resonance could be the messenger particle for gravity itself, the elusive graviton. In this breathtaking vision, the entire symphony of the cosmos, every particle and every force, emerges from the harmonious vibrations of these infinitesimal strings. But there is a profound catch, one that directly connects back to Kaluza-Klein. For the mathematics of these vibrations to be consistent, for the cosmic symphony to avoid disastrous discord, the strings cannot simply vibrate in our familiar 3 dimensions of space. The equations only work if the universe provides more room, more avenues for vibration. String theory demands extra spatial dimensions, not just one, as Kaluza proposed, but typically 6 or 7 additional ones, curled up into intricate, complex shapes at every point in our familiar reality. These are not large, expansive dimensions we could travel through. They are compactified, hidden geometries far smaller than an atom. Think of it like this. A guitar string stretched across our 3-dimensional room can only produce a limited set of sounds. But if that string could also vibrate into the tiny, coiled space inside the body of the guitar, it would gain a whole new universe of harmonic possibilities. The extra dimensions in string theory are that resonant chamber. They provide the necessary mathematical space for the strings to vibrate in all the precise ways needed to generate the diverse particles and forces we observe. This framework does not merely tolerate the idea of hidden dimensions, it is built upon them. They are the essential architectural feature that allows the theory to exist at all. And in doing so, string theory creates a natural, elegant home where gravity's peculiar weakness might finally find its explanation. If the strings whose vibrations produce the other forces are confined to our 3-dimensional slice of reality, while the strings that produce gravity are free to vibrate and spread their influence through all the dimensions, including the compactified ones, then gravity's apparent feebleness in our world becomes a geometric inevitability. Its strength is simply diluted across a broader hidden landscape. In this way, string theory weaves gravity back into the same fundamental tapestry as electromagnetism and the nuclear forces, not as an outsider, but as a different vibrational note in a far grander, multidimensional symphony. The mathematics of strings opened a door, but the brane-world scenario steps through it into a cosmos of breathtaking possibility. This idea proposes that our familiar 3-dimensional universe is not the full extent of reality. Instead, it is a vast membrane, a 3-dimensional sheet physicists call a brane, suspended within a higher dimensional arena known as the bulk. Picture our entire cosmos, every galaxy, every star, every one of us as existing on the surface of this immense floating membrane. We are embedded within it, like microscopic life forms living within the thin skin of a soap bubble. This is not just a poetic metaphor. It is a serious geometric model with profound implications for every force we know. In this picture, most of the forces that govern our daily reality are stuck on the brane. The particles of light, the carriers of electromagnetism, are like paint that cannot leave the surface of the canvas. The strong and weak nuclear forces are similarly confined. They define the rules of our local reality, but they cannot venture off our membrane into the wider bulk. Gravity, however, plays by a different set of rules. According to this scenario, gravity is not bound to our brane. The graviton, the hypothetical particle of gravity, is like a tiny droplet of water on that soap bubble's surface. It can seep through, its influence spreading out into the hidden higher dimensional space around us. This single, elegant shift in perspective transforms gravity's weakness from a mystery into a geometric necessity. If gravity's lines of force are free to spread out into the extra-dimensional bulk, then what we experience on our brane is only a fraction of its true strength. It is diluted, like the faint scent of a flower that has permeated a large room. The vivid models developed by theorists like Lisa Randall and Raman Sundram show mathematically how this leakage could precisely account for the staggering difference in strength between gravity and the other forces. Our universe feels gravity as the faintest whisper not because it is inherently weak, but because most of its voice is echoing in chambers we cannot see. This means the true, fundamental strength of gravity, out there in the full bulk of reality, could be just as potent as electromagnetism. We are simply experiencing a pale shadow of its full power, a shadow cast by the hidden architecture of the cosmos itself. The brane world is more than a theory. It is a new way of seeing our place in existence. It suggests we are not at the center of a vast, empty arena, but are inhabitants of a structure, a dynamic surface within a richer, deeper spatial ocean. What other phenomena, what other cosmic mysteries might be explained by this simple, radical idea that we are living on a membrane in a much larger reality? The true power of gravity might be echoing in rooms we cannot enter. To grasp how this leakage makes gravity so feeble in our world, we need a simple, physical analogy. Picture a single light bulb hanging in the center of a completely dark, empty room. When you turn it on, light radiates outward in all directions, filling the three-dimensional space. Its brightness, the intensity of light hitting your eyes, follows a simple rule. It diminishes with the square of the distance. Move twice as far from the bulb, and the light appears only 1/4 as bright. This is the familiar way influence dilutes in our three-dimensional world. Now, let us reshape reality. Imagine that same light bulb, but now it exists in a universe with one extra, hidden spatial dimension. The light no longer spreads out just in length, width, and height. It also radiates into this fourth dimension. From our limited, three-dimensional perspective within that cosmos, the light would appear dramatically dimmer, almost ghostly. We are only intercepting a fraction of the total light, because most of its energy is flowing into a direction we cannot perceive. This is the core idea of volume dilution. Gravity, according to the brane world scenario, is that light bulb. Its influence carried by gravitons is not confined to our three-dimensional membrane. It spills out into the extra-dimensional bulk. The lines of gravitational force have more room to spread, so by the time they reach another object on our brain, like Earth pulling on the moon, their grip feels incredibly weak. The mathematics behind this is elegant in its logic. The strength of a force is tied to how densely its lines of influence are packed. In three dimensions, those lines spread out over the surface of an ever-expanding sphere. Add more dimensions, and they spread out over the hypersurface of a higher dimensional sphere, which has vastly more volume. The lines become far more thinly distributed, and the force feels correspondingly fainter. This transforms gravity's greatest puzzle into a potential measuring stick. The precise amount of its weakness could, in principle, tell us about the size and shape of those hidden dimensions. It is not a mysterious flaw in nature's design. It is a direct signature of a larger geometric reality, a faint echo of the full symphony happening just beyond the walls of our perception. But how small would these hidden dimensions actually be? The answer is almost incomprehensibly tiny. In the original Kaluza-Klein picture, and in many versions of string theory, the extra dimensions are thought to be curled up at a scale known as the Planck length. This is about 10 to the power of -35 meters. To grasp that number, consider a single proton, one of the particles in an atom's nucleus. Now imagine dividing that proton by 1 billion, and then dividing that result by another billion. The Planck length is smaller than that. At such a minute scale, these dimensions are completely hidden from our instruments and our everyday experience. They are woven into the quantum foam of spacetime itself. A classic analogy is that garden hose stretched across a field. From a distance, it appears as a simple one-dimensional line. Only upon extremely close inspection would you discover its circular cross-section. Our perception of the cosmos is like that distant view. We lack the resolution to see the tiny, coiled geometry at every point. Yet the story does not end there. Some of the more daring brane world models propose a thrilling alternative. What if at least one of these extra dimensions is not Planck scale small? What if it is significantly larger, perhaps as big as a fraction of a millimeter? This is not a random guess. It emerges from a beautiful piece of reasoning. If gravity's strength is diluted because it spreads into a large extra dimension, then the size of that dimension directly determines how much dilution occurs. By working backward from gravity's known weakness, theorists can calculate how big a hidden dimension would need to be to produce the exact feebleness we measure. Remarkably, the math allows for a dimension that is just within the realm of experimental testing. A dimension 1/10 of a millimeter across is still microscopic to human eyes, but it is a colossal canyon compared to the Planck scale. It is a size we can actually probe. This possibility flips the entire experimental search on its head. We might not need a particle collider the size of a solar system to create the energies needed to see these dimensions. Instead, we could detect their presence through gravity itself, by measuring its behavior with exquisite precision at distances smaller than a millimeter. If gravity begins to behave differently, if it strengthens slightly when objects are brought incredibly close together, that deviation would be the signature of a hidden dimension opening up, a place where gravity's lines of force are no longer free to completely escape. The search for these dimensions, then, becomes a hunt not for gigantic energies, but for the most delicate of whispers in the quietest corners of space. This hunt for hidden geometry is not confined to chalkboards and equations. It has moved into some of the quietest, most precise laboratories on Earth. Here, scientists are not building colossal particle smashers. They are crafting instruments of breathtaking sensitivity, designed to listen for the faintest sigh of gravity at distances smaller than a human hair. The goal is disarmingly simple yet profoundly ambitious: to measure the gravitational pull between two objects brought incredibly close together, searching for any tiny deviation from the law that has governed our cosmos since Newton. If gravity strengthens ever so slightly at submillimeter scales, it would be a seismic discovery. It would mean that as the gaps close, the lines of gravitational force have less room to escape into a hidden dimension. That extra dimension, in effect, would begin to close off, concentrating gravity's influence back into our familiar three-dimensional world. This subtle change would be the direct, experimental signature of a larger reality. One of the pioneering efforts in this extraordinary search is the EOT-WASH group at the University of Washington. For decades, they have refined an instrument called a torsion balance. Imagine a thin, horizontal bar suspended by an even thinner fiber, like a perfectly balanced compass needle floating in a vacuum chamber. At each end of this bar hangs a test mass. Nearby, but not touching, are larger source masses that can be moved with exquisite control. The idea is to measure the almost imperceptible twist in that fiber caused by the gravitational attraction between the test masses and the source masses as they are brought within a whisper of each other. To isolate this signal from the cacophony of the everyday world is a monumental feat of engineering. The experiments run in a vacuum to eliminate air currents. They are shielded from magnetic and electrostatic interference. They compensate for the seismic vibrations of the Earth itself. The sensitivity is staggering. These instruments can measure forces so small they are equivalent to the weight of a single bacterium. They are, in essence, listening for the universe's quietest secret. Every tremor of a distant truck, every shift in atmospheric pressure, is a roar compared to the whisper they seek. The results so far have set powerful limits. Gravity has been confirmed to obey the classical inverse square law down to distances of about 52 micrometers. That is smaller than the width of a human hair. No extra dimension has yet announced itself within that realm, but the search is far from over. Each new experiment pushes the frontier a little further into a quieter, smaller domain. This is the cutting edge of experimental physics. It is a meticulous, patient hunt for a geometric echo, a direct test of whether the deepest weakness in nature is simply the shadow of a hidden, more spacious world. While some listen for gravity's faintest whispers, others seek to tear the fabric of space itself. The search for hidden dimensions also unfolds within the world's most powerful machines, where particles are hurled at each other at nearly the speed of light. At the Large Hadron Collider beneath the Swiss-French border, protons collide with energies that recreate conditions a fraction of a second after the Big Bang. Here, physicists look for something extraordinary in the debris of these microscopic cataclysms, a clue known as missing energy. The concept is both simple and profound. When two protons smash together, their immense energy is converted into a shower of new particles, all carefully tracked by massive detectors. The total energy and momentum before the collision must equal the total after, a fundamental bookkeeping rule of the universe. But what if something is produced in that collision that simply vanishes from our detector? According to the brane-world idea, that something could be a graviton. If the collision is violent enough, it might briefly create a particle of gravity. And since gravity is not confined to our brain, that graviton could immediately zip off into the hidden bulk dimensions, taking a precise amount of energy and momentum with it. From our perspective, locked on our three-dimensional membrane, that energy would simply disappear. It would be an accounting error in the heart of the collision, a clear sign that something was created and then escaped to a place we cannot see. This missing energy signature is one of the most sought-after clues in modern particle physics. It is a ghost in the machine, a silent testimony to a larger reality. An even more dramatic possibility exists at the highest energies. Some theories suggest that a sufficiently powerful collision could warp local spacetime so intensely that it pinches off, forming a microscopic black hole. This would not be the gravitational monster of science fiction. It would be an ephemeral speck, smaller than a proton, that would evaporate in an instant through a process called Hawking radiation, leaving behind a distinctive burst of particles. The creation of such an object, even for a fleeting moment, would be revolutionary. It would prove that the extra dimensions are not just mathematical curiosities, but are real and accessible at energies we can produce. The geometry of those hidden dimensions would determine the energy required and the way the micro-black hole decays. While neither missing energy nor micro-black holes have been observed at the Large Hadron Collider, their continued absence is itself a valuable result. It tells us that if extra dimensions exist, they are either smaller or configured in ways that place them just beyond our current reach. This high-energy frontier represents a complementary path in the quest, one that seeks not to measure gravity's subtle weakness, but to use raw power to momentarily breach the walls of our dimensional prison, hoping to catch a glimpse of what lies beyond. The search for hidden dimensions reaches far beyond the quiet of earthbound labs and the fury of particle collisions. It extends to the very edges of the observable cosmos, where two great shadows dominate our universe: dark matter and dark energy. These are not just gaps in our knowledge, they are profound, dominating presences that shape the fate of everything. Could it be that their mysterious nature is also a clue, a hint that we are not seeing the full geometric picture? Some of the most compelling theories suggest that the same hidden architecture that might explain gravity's weakness could also be the key to unlocking these cosmic enigmas. Take dark matter first. We know it exists because of its powerful gravitational grip on galaxies and clusters, yet it emits no light and seems to pass through ordinary matter like a ghost. What if this ghostliness has a geometric explanation? Imagine our universe as one three-dimensional membrane floating in the bulk. Now, picture a second membrane, a parallel brane, hovering a tiny distance away in a hidden dimension. This neighboring brane could be home to an entire universe of particles that feel their own forces, completely separate from our electromagnetism and nuclear forces. But gravity, leaking through the bulk, can bridge the gap, From our perspective, the matter on that nearby brane would be invisible, intangible, yet its gravitational pull would be felt unmistakably in our world. It would behave exactly like dark matter, a massive, pervasive presence that interacts with us only through gravity. This elegant idea transforms dark matter from a missing ingredient in our universe into a signpost pointing toward a neighboring reality, just a whisper away in a dimension we cannot traverse. Then there is dark energy, the even more perplexing force causing the expansion of the universe to accelerate. Its repulsive push seems to be an intrinsic property of empty space itself, a constant energy woven into the vacuum. Could this, too, be a symptom of a larger geometry, the dynamics of the bulk space, the higher dimensional arena in which our brane floats, might exert a constant pressure on our membrane? Think of our universe as a flexible sheet suspended in a flowing river. The currents and tensions in that surrounding water could gently stretch the sheet, causing it to expand at an ever-increasing rate from our point of view within it. In this framework, dark energy is not a mysterious substance within our universe, but a consequence of our universe's placement and interaction with the full, hidden spatial landscape. The cosmological constant, that enigmatic number driving acceleration, could be a measurement of the bulk's influence. This widens the lens to a breathtaking scale. The weakness of gravity, the ghostly nature of dark matter, and the repulsive push of dark energy might not be three separate puzzles. They could be interconnected symptoms of a single, deeper truth, that our cosmos is a dynamic structure within a richer, multidimensional reality. The faintest force becomes a thread, connecting the behavior of the smallest particles to the destiny of the largest cosmic structures. It suggests a hidden architecture where the rules are written not just in the particles we see, but in the folded, secret geometry of space itself. If true, then every galaxy cluster, every measurement of the universe's expansion, is a message in a code we are only beginning to decipher, a code that speaks of dimensions beyond our perception. String theory's hidden dimensions open a door, but behind it lies an even more staggering vista. The mathematics does not point to a single, unique universe with our exact laws. Instead, it suggests a nearly infinite landscape of possibilities, a cosmic archipelago where each island is a universe with its own distinct physical constants. This is the multiverse hypothesis. Within this vast ensemble, the strength of gravity, the mass of an electron, even the number of dimensions could vary wildly from one universe to the next. Our cosmos, with its specific, finely tuned numbers, would be just one possibility among an unimaginable multitude. In this context, gravity's profound weakness is no longer a puzzle demanding a single, elegant equation. It becomes a contingent fact, a local bylaw in our particular cosmic neighborhood. The question shifts dramatically. We are not asking why gravity must be weak in any possible universe. We are asking why it is weak in this one, the universe we happen to inhabit. This leads to a profound and sometimes controversial line of reasoning known as the Anthropic principle. In its simplest form, it states that the universe we observe must be compatible with the existence of observers. We should not be surprised to find ourselves in a universe capable of producing stars, planets, and ultimately, life. Consider gravity's role. If gravity were significantly stronger relative to the other forces, the universe would be a very different place. Stars would burn their fuel at a ferocious rate, flickering out in mere millions of years instead of billions, leaving no time for planetary systems to mature and complex chemistry to arise. Planets themselves might be crushed under their own weight or never form at all from the cosmic debris. In a universe where the forces are balanced differently, the delicate chain of events that leads from the Big Bang to conscious life might be broken at the very first link. So perhaps we find ourselves in a universe with remarkably weak gravity for a simple, observational reason. It is a universe where the conditions are just right for us to be here to notice it. This is a philosophical earthquake. It reframes the entire investigation. The mystery of gravity's feebleness transforms from a why question of fundamental law into a where question of cosmic address. We are not uncovering a necessary truth of all existence, but rather a statistical selection effect. We live in one of the potentially rare universes in the multiversal landscape where the numbers allow for galaxies, solar systems, and beings who can look up and wonder about the forces that bind them. This does not make the question less meaningful. It makes our answer part of a larger story about our place in a reality of breathtaking scope. The weakness of gravity, then, might be the most personal clue of all. It is not just a sign of hidden dimensions, but a signature of a universe that has the specific architecture necessary to ask the question in the first place. What does our very existence tell us about the landscape of all possible realities? The dream of a single equation, a master key to unlock the cosmos, has always been physics' most profound ambition. This is not just about solving puzzles. It is a quest for a deeper kind of beauty, a conviction that beneath nature's bewildering complexity lies an elegant, unified simplicity. The weakness of gravity, so long a stubborn anomaly, becomes something far more significant in this light. It is not a flaw to be patched, but a crucial clue pointing toward a grander, more harmonious design. The drive to understand hidden dimensions is fueled by this very desire for unity. It asks a breathtaking question. What if all the forces, all the particles, are not separate actors but different expressions of a single underlying reality, written in the geometry of a higher dimensional space? This is where string theory evolves into its most ambitious form, a framework known as M-theory. While the details are mathematically formidable, the vision is stunningly clear. M-theory proposes that our 11-dimensional universe, with its 3 large dimensions, 1 of time and 7 curled-up dimensions, is not the only possibility. It suggests that all the different versions of string theory we have discovered are like different projections or shadows of a single, deeper theory, much like a 3-dimensional cube can cast a variety of 2-dimensional shadows. In this unified 11-dimensional geometry, everything is connected. The vibration of a fundamental membrane or brane in this space can manifest as a particle, a force, or even an entire universe. Gravity's unique role and its apparent weakness are not arbitrary choices. They emerge naturally, inevitably, from the specific way our particular cosmic membrane is embedded and folded within this grander arena. The force's feebleness in our world is a direct geometric consequence, a signature of how the full, unified reality projects onto our limited slice of existence. This pursuit of a unified framework is often described in terms of mathematical beauty. Edward Witten, a leading figure in this quest, has spoken of searching for the deep simplicity that underlies the apparent complexity of the natural world. For many theorists, the equations themselves have a kind of compelling elegance and inevitability that feels like a guide toward truth. The decades-long pursuit of extra dimensions, then, is not merely a technical exercise. It is a philosophical and aesthetic journey. It is the belief that the universe, at its most fundamental level, is not a collection of unrelated parts but a coherent, beautiful whole. Gravity's puzzling weakness is the thread that, when pulled, begins to unravel not just its own mystery, but the entire tapestry. It justifies the search because it promises a reward greater than any single answer. It promises a vision of cosmic unity where every force, every speck of matter finds its place in a single, elegant geometric story. In this view, we are not just deciphering laws. We are learning to read the architecture of existence itself. Our quest to understand gravity's faint whisper leads us to a profound and unsettling possibility. The investigation is no longer just about physics. It becomes a deep philosophical inquiry into the very nature of reality, and the severe limits of our own perception. If the core explanation for the universe's most fundamental imbalance lies in dimensions we cannot see or experience, then what does that say about everything we consider real? Our entire existence, from the ground beneath our feet to the distant light of galaxies, is filtered through the narrow window of our three spatial dimensions. We are, in a very literal sense, trapped within a slice of the full cosmos. This realization echoes one of philosophy's oldest and most powerful thought experiments, Plato's allegory of the cave. In that story, prisoners are chained from birth inside a dark cave facing a wall. Behind them, a fire casts shadows of objects they can never see. For those prisoners, the flickering shadows on the wall are the sum total of reality. They have no concept of the three-dimensional objects, the fire, or the world outside the cave that creates those shadows. Our situation, if these theories are correct, is hauntingly similar. The particles we detect, the forces we measure, even the stars we observe, may be mere projections or shadows of a richer, more complex reality playing out in a higher dimensional arena. The force of gravity, in this analogy, is the faint clue, the distant echo, or the slight distortion in the shadow that hints at the existence of the objects and the light source behind us. This challenges our most basic intuitions. We trust our senses to report an accurate picture of the world, but they evolved to navigate survival on a three-dimensional landscape, not to perceive the full architecture of the universe. Our notion of what is real is built from this limited data. It is like a being that lives its entire life on the two-dimensional surface of a pond, only aware of ripples and reflections, completely ignorant of the rich world of depth, fish, and plants that exists below and above the waterline. That being would have a true but radically incomplete understanding of its reality. The search for hidden dimensions forces us to confront the same humbling truth. We are the pond skimmers of the cosmos. Our powerful mathematics and ingenious experiments are our tools for inferring the shape of the deeper waters. This line of thinking naturally leads to a cascade of reflective questions. If something as fundamental as the strength of a force can be dictated by geometry we cannot perceive, how many other aspects of reality are similarly hidden? Are there phenomena we dismiss as mysteries or anomalies that are simply the three-dimensional shadows of processes we lack the framework to understand? Could concepts like consciousness or the arrow of time have explanations that reside in the fuller geometry of the cosmos? The investigation into gravity's weakness thus expands into a meditation on the limits of human knowledge itself. It suggests that the ultimate nature of reality may be, in principle, partially or even largely inaccessible to beings like us, confined as we are to our specific dimensional slice. This is not a cause for despair, but for a profound shift in perspective. It transforms science from a process of simply cataloging what we see into a daring act of inference and imagination, of reading between the lines of reality to reconstruct a hidden text. Our place in this possibly multidimensional existence is both humbling and strangely empowering. We are not at the center of a simple, transparent stage. We are inhabitants of a vast, layered, and deeply mysterious structure, using the faintest of clues, like the unexpected gentleness of gravity, to piece together a map of the unseen. This journey asks us to hold two truths at once: to fully trust the rigorous, empirical world revealed by our instruments, while remaining open to the breathtaking possibility that it is only a fragment of a much grander, more astonishing whole. The profound possibility of hidden dimensions naturally leads to a tantalizing question with implications far beyond pure science. If these extra folds of space are real, could humanity ever learn to access them, or even use their geometry to transform our capabilities? While this ventures into the realm of speculative thought, it is a speculation grounded in the logical extension of the very theories we have been exploring. It invites us to consider how solving the deepest riddles of nature can unlock technological horizons we can barely envision today. One of the most captivating ideas involves the nature of travel. Our current understanding of physics places a firm speed limit on the universe, the speed of light. Crossing interstellar distances would take millennia with conventional propulsion. But if our universe is a membrane within a higher dimensional bulk, a fascinating loophole emerges. It might be possible, in theory, to create a shortcut. Imagine 2 points on a vast sheet of paper. The shortest distance between them is a straight line across the surface. But if you could bend the paper through a third dimension, you could bring those points almost into contact, creating a tunnel or a bridge through the bulk. In cosmological terms, such a structure is known as a wormhole. The mathematics of general relativity allows for their existence, but they would require exotic forms of matter with negative energy to stabilize them, something we have never observed. The inclusion of extra dimensions in models like string theory or brane-worlds provides a new landscape where such geometric manipulations might be more plausible. The energy required to open or stabilize a passage could be intimately tied to the properties of the hidden dimensions themselves. This is not a blueprint for a starship engine, but it illustrates a profound principle. Mastering the geometry of space-time, understanding its full multidimensional architecture, could one day redefine what travel means, turning distant stars from unreachable points of light into potential destinations. Beyond travel, the very way we harness energy could be transformed. Consider the concept of transduction, converting energy from one form to another. In our three-dimensional world, we capture solar radiation, harness chemical bonds, or split atoms. But if gravity's true strength is concentrated in the bulk, accessing even a fraction of that concentrated power from our brain could represent an energy source of cosmic scale. More subtly, the compactified dimensions of string theory are not empty. They have a precise shape, a Kaluza-Klein manifold, and that shape determines the properties of particles and forces in our world. In a future where we could somehow measure or even influence that hidden geometry, we might learn to tune the fabric of reality itself, potentially engineering the properties of materials or forces in ways that seem like magic today. It is crucial to state clearly that these are thought experiments, not predictions. They are exercises in connecting deep theoretical principles to their ultimate technological potential, highlighting a historical pattern. The discovery of electromagnetism was once a curious phenomenon involving amber and lodestones. No one at the time could have predicted it would lead to a global grid, instant communication, and the digital age. Similarly, unraveling the quantum mechanics of the atom gave us the semiconductor and the modern world. Solving the mystery of gravity's weakness and uncovering the geometry of hidden dimensions could be a discovery of that same monumental caliber. Its applications are unimaginable to us now because they would operate on a foundational level, manipulating the very stage upon which all physics plays out. This long-term vision sparks the imagination. It suggests that our greatest limitations, like the vastness of space or the scarcity of energy, may not be absolute laws, but reflections of our incomplete understanding. The quest to explain a single, faint force becomes a journey toward potentially mastering the hidden architecture of existence itself. What new chapters in our story might we write if we ever learn to read the full geometry of the cosmos? Yet for all its breathtaking scope and mathematical elegance, this vision of hidden dimensions faces a formidable wall of criticism. The most significant challenge is stark and undeniable, a direct confrontation with the scientific method itself. After decades of intense theoretical work, there is still no direct, experimental evidence for the existence of extra dimensions or the fundamental strings that would require them. The Large Hadron Collider has not observed missing energy or microscopic black holes. exquisitely sensitive tabletop experiments have not yet detected gravity strengthening at tiny scales. This absence of proof is not a minor footnote. It is the central tension in the entire endeavor. Science advances through testable predictions, and so far, these ideas have remained frustratingly beyond the reach of our most powerful instruments. Some critics, like mathematician Peter Woit, argue this is not a temporary setback but a fundamental flaw. In his view, a theory that does not make clear, unique predictions that can be experimentally confirmed or refuted risks drifting from the realm of science into the domain of mathematical philosophy, beautiful but ultimately untethered from physical reality. The concern is about falsifiability, the essential principle that a scientific idea must be capable of being proven wrong. If a theory is so flexible that it can accommodate almost any experimental outcome by adjusting its many parameters, critics ask, how can we ever truly test it? This leads to the challenge of predictive power. String theory, in its current form, is not a single, precise theory but a vast landscape of possible solutions, each corresponding to a universe with different properties. With so many potential configurations, it becomes extraordinarily difficult to point to one specific, non-generic phenomenon and say, this and only this must happen if the theory is true. The physicist Lee Smolin has raised this point thoughtfully, suggesting that the pursuit may have become disconnected from the empirical grounding that has historically driven physics forward. He and others propose that alternative avenues like loop quantum gravity, which attempts to quantize spacetime itself without extra dimensions, deserve equal attention. Furthermore, the sheer mathematical complexity of these theories presents its own hurdle. The equations describing Calabi-Yau manifolds and brane dynamics are among the most intricate in all of physics, accessible only to a small number of specialists. This complexity can create a barrier, making it harder for the broader scientific community to engage with, critique, and build upon the ideas. It also raises a philosophical question: are we discovering the universe's innate complexity? Or are we constructing an increasingly elaborate mathematical edifice to explain a few stubborn numbers? The hierarchy problem itself, the original clue, is also attacked from other angles. Competing explanations like supersymmetry propose a different solution entirely, suggesting every known particle has a heavier, unseen superpartner. This symmetry could naturally cancel out certain extreme quantum effects and stabilize the vast gap between forces, all within our familiar four-dimensional spacetime. Experiments have not yet found these superpartners either, keeping that alternative alive but unconfirmed. This landscape of criticism is not a sign of failure. It is the sound of healthy, rigorous science at work. The path from a fascinating clue like gravity's weakness to a settled truth is never a straight line. It is a winding road paved with bold proposals, fierce debate, and relentless testing. The profound skepticism surrounding extra dimensions serves a vital purpose. It forces theorists to sharpen their ideas, to search for that one crisp, undeniable prediction that could break the stalemate. It reminds us that the most captivating stories in science are not those told with certainty, but those written in the challenging, uncertain, and utterly necessary language of doubt. The absence of a definitive signal for extra dimensions does not leave physics without a map. Other compelling routes on the theoretical landscape aim to solve the same profound puzzle, offering radically different visions of cosmic architecture. One of the most elegant and long-standing alternatives is supersymmetry. This theory proposes a breathtaking symmetry at the heart of nature, where every known particle in the standard model has a hidden, heavier twin, a superpartner. An electron would have a selectron, a quark would have a squark, and the photon would have a photino. This is not just an exercise in doubling the particle zoo. The mathematical beauty of supersymmetry is that it provides a natural, elegant solution to the hierarchy problem. The quantum fluctuations of these superpartner particles would perfectly cancel out the extreme, destabilizing effects that otherwise make the Higgs boson's mass, and by extension the entire scale of the weak force, so unnaturally fine-tuned compared to gravity. In a supersymmetric universe, the vast gulf between the force strengths becomes stable and explained, all within our familiar four-dimensional spacetime. It is a compelling vision of hidden order, not hidden space. Yet, like the search for extra dimensions, the hunt for these superpartners has so far come up empty. The Large Hadron Collider has probed energies where many theorists expected to find them, and they have not appeared. This does not rule supersymmetry out entirely, but it pushes its possible realization into higher, more elusive energy realms, testing the patience and creativity of the field. Other ideas have risen and evolved. Concepts like Technicolor proposed that the Higgs boson is not a fundamental particle, but a composite object bound by a new, powerful force, analogous to how protons are bound by the strong nuclear force. This would also alter the hierarchy, though such models have faced significant challenges in matching observed data. Even within the realm of extra dimensions, there are competing geometries. The AD model, named for theorists Arkani Hamed, Dimopoulos, and D. Volley, proposes that the extra dimensions could be as large as a fraction of a millimeter, but that gravity alone propagates through them, while all other forces are strictly confined to our brane. This is a different architectural blueprint from the warped geometries of models like Randall-Sundrum, yet it aims to solve the same core problem of gravity's dilution. This rich tapestry of competing ideas is not a sign of confusion, but of a field vibrantly alive. The profound weakness of gravity is the engine driving this entire endeavor. It is the stubborn clue that refuses to be ignored, forcing the brightest minds to propose ever more inventive and daring structures for reality. Each theory, from supersymmetry to Technicolor to varied brane worlds, represents a different answer to the same fundamental question, written in a different mathematical language. This ongoing dialogue, sometimes contentious but always rigorous, is the true process of discovery. It means that while hidden dimensions are a breathtaking possibility, they are not the only path forward. The universe has not yet tipped its hand. The continued absence of evidence is in its own way a form of data, pruning the landscape of possibilities and guiding the next generation of questions. This moment in physics is not about a single answer waiting to be found, but about holding multiple profound possibilities in mind, each with the potential to redefine everything we know. The journey to explain a single, faint force has opened not one door, but many, revealing a labyrinth of theoretical splendor where the final truth remains gloriously out of reach. At the heart of the particle world lies a field more crucial than any other. The discovery of the Higgs boson in 2012 was a triumph of human ingenuity, confirming a decades-old theory about how the universe acquires its substance. Yet, this monumental achievement did not simplify our cosmic story. Instead, it sharpened the mystery of gravity's weakness into an even more urgent question. To understand why, we need to see what the Higgs truly does. Imagine empty space not as a true void, but as filled with an invisible, treacle-like field, the Higgs field. As fundamental particles move through this cosmic medium, they interact with it. Some particles, like photons, zip through unaffected, remaining massless. Others, like quarks and electrons, drag through the field as if wading through deep water, and this resistance is what we experience as their mass. The Higgs boson is the ripple, the detectable excitation in that field. Its discovery proved the field's existence, completing our picture of how matter gets its heft. But this elegant mechanism comes with a profound and unsettling caveat. The Higgs boson itself has a mass, and within the mathematics of quantum field theory, that mass is terrifyingly unstable. It is subject to what physicists call quantum corrections. Virtual particles constantly flickering in and out of existence from the quantum vacuum should contribute enormous energy to the Higgs field. Think of it like a delicate scale constantly being bombarded by heavy stones from all sides. To keep the scale balanced, to keep the Higgs mass as small as we measure it, would require an almost miraculous cancellation, each stone from one side perfectly matched by an identical stone from the opposite side, to a precision of 1 part in a million billion. This absurd level of fine-tuning strikes most physicists as deeply unnatural. It is the hierarchy problem incarnate, now starring the Higgs boson. The puzzle is no longer abstract. It is embodied in this one fragile particle. Its precarious lightness is directly connected to the vast gulf between the force strengths. If the Higgs mass were pulled to the enormous scales suggested by quantum gravity, the weak nuclear force would be immensely stronger, utterly collapsing the delicate balance that allows atoms and chemistry to exist. So the Higgs is not just another particle, it is a keystone in the arch of reality. Its stability, or rather its inexplicable, fine-tuned stability, is the very thing that allows our universe to have stars, planets, and life. This is why its discovery intensified the search for new physics. The prevailing sentiment is that nature abhors fine-tuning. There must be a mechanism, a new symmetry, or a new geometric principle that naturally protects the Higgs mass from these quantum storms. Supersymmetry is one proposed guardian, with its superpartner particles providing the perfect cancellations, but the idea of extra dimensions offers another compelling shield. In some brane-world scenarios, the reason the Higgs mass remains small in our world is because it is actually a projection of a field that lives in the higher dimensional bulk, where the rules of quantum corrections are different. Its properties are shaped by the full, hidden geometry, making its observed lightness in our slice a natural outcome, not a miraculous accident. This makes the Higgs boson a central character in our drama and a crucial guide for future exploration. Every new collision at the Large Hadron Collider, every precise measurement of how the Higgs decays or interacts, is a search for tiny deviations from the standard model's predictions. A slight anomaly in its behavior could be the fingerprint of those hidden dimensions or of supersymmetric partners, the first tangible clue to the architecture that stabilizes our entire reality. The faintest force and the mass-giving particle are now threads in the same tapestry, pulling us toward a deeper layer of truth hidden just beneath the quantum surface. An ant can walk safely along a high-voltage power line, completely untouched by the immense energy surging just millimeters away. It feels no shock, no jolt, because it is only in contact with that single line. The powerful electromagnetic field surrounding the cable does not affect the ant, as it is not bridging the gap to another line or to the ground. This simple, vivid image is a perfect key to understanding our own place in the cosmos. In the brane-world picture, our entire universe is like that ant, living entirely on a single conductive line. All the forces we know and interact with everyday electromagnetism, the strong and weak nuclear forces, are like that powerful current. They are immense, but they are confined strictly to our membrane, our three-dimensional line. We are embedded in them, shaped by them, yet completely insulated from anything beyond. Now think about the space around that power line. There is air, there is the faint hum of the field, there are subtle breezes. Gravity, in this analogy, is that faint breeze. It is not confined to the line. It can come from any direction, from the insulated space around the cable, from the wider world. That surrounding space is the bulk, the higher dimensional arena. The breeze is gentle, diluted, because it spreads out through all that open volume. Its true source might be powerful, but by the time it reaches the ant on the line, it is just a whisper. This makes the staggering difference in strength suddenly intuitive. The forces on our brain are concentrated, direct, and overwhelmingly powerful within their domain, like the electricity in the wire. Gravity, free to wander the bulk, is diffuse and faint from our limited perspective. The ant never questions why the breeze is so much weaker than the current it walks on. The difference is not in the fundamental nature of the forces, but in the geometry of their playground. One is channeled, the other is liberated. This analogy helps us visualize a reality where our most direct experiences are not the full story. We are so focused on the powerful currents of our three-dimensional existence that we might miss the subtle, universal breeze that hints at a far larger landscape. It transforms an abstract mathematical concept into a sensory experience. You can almost feel the hum of the confined forces and the gentle, omnipresent tug of gravity, understanding not just with your mind, but with a deeper intuition, why the faintest pull might be the most important clue we have. The faint breeze we feel might also carry echoes from a far larger sea. In 2015, humanity achieved something once thought impossible. We directly detected gravitational waves, the ripples in spacetime itself, caused by cataclysmic events like colliding black holes. This was not just a confirmation of Einstein's genius. It opened a brand new sense, a way to hear the universe's most violent symphonies. But what if this new sense could also listen for the architecture of the hidden rooms? Could these space-time ripples carry a faint signature, a subtle distortion, telling us they have traveled through more than just our three familiar dimensions? The idea is as thrilling as it is subtle. When gravitational waves propagate, they are not just waves in empty space. They are oscillations of the geometry that contains everything. If that geometry has extra compactified dimensions, the waves might interact with them in ways that leave a trace. Some theoretical models suggest these ripples could mix with hypothetical scalar fields, new kinds of energy that might permeate the bulk. This mixing could very slightly alter how the waves lose energy as they travel across cosmic distances. Other models propose that the speed of gravitational waves could be minutely different from the speed of light if they traverse a higher dimensional landscape, even for an instant. The key word here is minutely. The initial detections by LIGO and Virgo have been a stunning triumph for classical general relativity in a four-dimensional universe. The waves arrived exactly when and how Einstein's equations predicted, with no obvious anomalies. But this alignment is not the end of the story. It is the establishment of a baseline, a perfect standard against which future, more sensitive ears can listen for the slightest whisper of deviation. Next-generation observatories like the space-based LISA mission or even more advanced ground-based detectors will catch waves from more distant, more ancient events. They will measure the ripples with unprecedented precision. In that finer data, scientists will scour for any tiny discrepancy, any hint that the waves behaved in a way that cannot be fully explained by the smooth fabric of a purely three-dimensional space. A single, statistically significant anomaly would be a revolution. It would suggest that gravitational waves are not just messengers of massive events, but probes of the universe's hidden geometry. They would become the most direct tool we have for sensing the bulk. This connects a monumental observational victory directly back to our core mystery. The very act of detecting gravity's dynamics, of feeling its ripples, has given us a potential instrument, a cosmic tuning fork, that might one day resonate with the shape of dimensions we cannot see. The silence so far is not a no. It is the deep quiet before we learn how to listen properly. The cosmological constant is gravity's ultimate and most profound embarrassment. We have grappled with its weakness compared to other forces, but this is a different kind of feebleness, a failure on the grandest scale. In the equations of general relativity, Einstein included a term he later called his greatest blunder, a factor representing the energy inherent to empty space itself. This is the cosmological constant. For decades it was thought to be zero, a mathematical curiosity. Then, in the late 1990s, astronomers made a shocking discovery. The expansion of the universe is not slowing down. It is accelerating, driven by a mysterious repulsive force. The best explanation for that force is a positive cosmological constant, a tiny but undeniable energy woven into the very fabric of the vacuum. This discovery earned a Nobel Prize and plunged physics into a crisis far deeper than the hierarchy problem. The observed value of this dark energy is incredibly small, but not zero. And that is where the true catastrophe lies. When we use our best theory of the quantum world to calculate how much energy should be bubbling in the vacuum from all those virtual particles flickering in and out of existence, we get a number. That number is not just a little off, it is wrong by a factor of 1 followed by 120 zeros. It is, without exaggeration, the worst theoretical prediction in the entire history of science. The discrepancy is so vast it is incomprehensible. If the predicted value were represented by the size of the entire observable universe, the actual measured value would be smaller than a single atom. This is not a minor tuning problem. It is a screaming declaration that our understanding of gravity and the quantum vacuum is fundamentally, catastrophically broken. The cosmological constant problem makes the hierarchy puzzle look simple by comparison. It tells us that empty space, the very nothingness between stars, should be seething with such unimaginable energy that the universe would have torn itself apart in a violent explosion moments after the Big Bang. Yet here we are in a cosmos that is gently, steadily accelerating apart. So why is the vacuum so eerily calm? This is where the geometry of hidden dimensions offers a radical and compelling shift in perspective. In our familiar three-dimensional world, vacuum energy is trapped, bottled up on our brain. Its colossal predicted pressure has nowhere to go, creating that impossible theoretical tension. But what if the vacuum, like gravity, is not entirely confined? What if the energy of empty space can also leak or dissipate into the extra-dimensional bulk? Imagine a pot of water boiling vigorously on a stove. In a sealed kitchen, the steam builds pressure until something breaks. But if you open a window, the steam escapes into the vast atmosphere outside, and the pressure inside the room remains manageable. In this analogy, our three-dimensional universe is the kitchen. The quantum vacuum is the boiling pot. The predicted cosmological constant is the dangerous buildup of steam. And the open window is a connection to the higher dimensional bulk. If the fabric of our brain allows even a tiny channel for that vacuum energy to seep away into the larger spatial arena, the effective energy density we measure in our world could be reduced from a universe-shattering level to the tiny, positive trickle we actually observe. The bulk acts as a cosmic pressure release valve. This elegant idea does something remarkable. It directly connects the two greatest failures in our understanding of gravity. The first is its inexplicable weakness on the scale of particles. The second is its inexplicable failure to react to the quantum vacuum's furious energy. Both problems stem from gravity's unique relationship with space itself, and both could find a unified explanation in the same geometric truth, that our universe is a membrane within a larger reality. The faint tug we feel between objects and the gentle push accelerating galaxies apart may be two different echoes of the same profound architectural feature, dimensions hidden from our view but essential to the stability of our entire existence. Our universe is not a lonely island, but one possibility in an ocean of nearly infinite alternatives. Within the framework of string theory, this idea becomes mathematically concrete through the concept of the landscape. This is not a physical terrain, but a vast, abstract space of possible configurations for the hidden dimensions. Each point in this landscape represents a specific way those extra dimensions can be curled and folded, a unique Calabi-Yau shape. And each distinct shape determines a different set of physical laws in the universe it describes. The number of these possible configurations is not just large. It is estimated to be around 10 to the power of 500. That is a 1 followed by 500 zeros, a number so vast it exceeds the count of atoms in the observable universe by an unimaginable margin. In this cosmic library, every possible variation of nature's constants exists somewhere on a shelf. Some universes might have gravity 1,000 times stronger, collapsing instantly into black holes. Others might have electromagnetism too weak to form stable atoms. Our universe, with its specific, finely tuned numbers, including the profound weakness of gravity, is just one volume in this infinite collection. This transforms the fundamental question from why our laws are the way they are to how our particular volume was selected from the library. This is the puzzle of vacuum selection. The vacuum here means the lowest energy state, the default setting of empty space for a given configuration of dimensions. Our quest is to understand the mechanism that picked our specific vacuum, our specific set of physical laws out of the endless options. One of the most compelling mechanisms proposed is eternal inflation. Picture the primordial cosmos not as a single exploding point, but as an eternally expanding, seething sea of energy, a multiversal foam. Within this frothing medium, pockets can suddenly drop to a lower energy state, like bubbles forming in a boiling pot. Each of these bubbles nucleates its own distinct universe, with its own random selection from the landscape of possibilities, its own unique vacuum. The inflating sea between bubbles continues to expand forever, constantly giving birth to new bubble universes, each with its own physics. In this breathtaking vision, our entire cosmos is one such bubble. The weakness of gravity, then, is not a necessary truth. It is a cosmic accident, a random roll of the dice in our particular bubble. We find ourselves in a universe with weak gravity because only in such a universe could galaxies, stars, planets, and ultimately observers like us ever arise. In bubbles where gravity is stronger, universes may flash into existence and collapse before anything complex can form. This idea, known as the Anthropic principle, offers a profound shift in perspective. It suggests we should not be surprised to find ourselves in a universe compatible with our existence. The search for a single, elegant equation that uniquely predicts our specific numbers might be misplaced. Instead, we may live in a cosmos of breathtaking plurality, where the laws of physics are local bylaws, not universal commandments. This does not make the mystery less profound. It expands it to a scale that challenges our very notion of a fundamental explanation. The faint tug of gravity becomes a personal signature, a clue not just to hidden dimensions, but to our specific address in a multiverse of staggering scope. What does it mean for our understanding of reality if the deepest parameters of existence are ultimately contingent, the result of a random cosmic draw? The search for a single set of rules has led physics to a deep and stubborn impasse. Our two most successful theories of the universe speak completely different languages, and gravity is the word they cannot translate. On one hand, we have quantum mechanics, a spectacularly precise description of the very small. It tells us the world is built from discrete, fuzzy particles and unpredictable probabilities, a realm where empty space seethes with fleeting energy. On the other, we have Einstein's general relativity, a majestic description of the very large. It tells us gravity is not a force at all, but the elegant curvature of a smooth, continuous spacetime. Each theory is triumphant in its own domain, yet they are fundamentally, mathematically incompatible. Attempting to combine them to describe gravity with the same quantum rules that govern every other force leads equations to produce nonsensical, infinite results. This is the core dilemma of quantum gravity, and it suggests our understanding of reality is fractured at the deepest level. The conflict becomes unavoidable only at unimaginably tiny scales and colossal energies, a realm defined by the Planck scale. To reach this domain, you would need to compress an object's mass into a volume so small that its gravitational pull becomes as strong as the other fundamental forces. This scale is about 10 to the power of -35 meters across. For comparison, if you enlarged a single atom to the size of the observable universe, the Planck length would be roughly the height of a tree. The energy required to probe this realm is similarly astronomical, a quadrillion times greater than what our most powerful particle colliders can produce. This is why we have never directly observed quantum gravity effects. We are trying to hear a whisper in a hurricane using instruments built for a much quieter world. The Planck scale represents the frontier where the smooth geometry of relativity must shatter into the probabilistic foam of the quantum, and our current mathematics simply cannot describe what happens there. This is precisely where the concept of extra dimensions offers a compelling pathway forward. The problem with quantizing gravity in our familiar 4 dimensions is that there is not enough room, mathematically speaking, for the equations to remain consistent. The calculations become plagued with infinities because the degrees of freedom, the ways the gravitational field can vibrate and interact, are too constrained. Introducing additional spatial dimensions, as string theory does, provides a larger mathematical arena. It gives gravity more room to breathe. Those curled-up dimensions offer new vibrational modes and pathways for interaction that can naturally cancel out the catastrophic infinities. In this framework, gravity is not an outsider refusing to play by quantum rules. It becomes a different vibrational pattern of a fundamental string, seamlessly unified with the other forces in a higher dimensional reality. The weakness we perceive in our 3-dimensional slice is then a direct geometric consequence of this unification, a signature of the full, hidden architecture. Therefore, gravity's puzzling feebleness is far more than an isolated curiosity. It is the most glaring symptom of the profound rift at the foundation of physics. The staggering gap between its strength and that of electromagnetism is a constant, nagging reminder that our 2 great descriptions of the universe are still strangers to each other. Solving the hierarchy problem is not a side quest. It is intrinsically linked to the monumental task of healing this fracture. Any theory that successfully explains why gravity is so weak must, by necessity, also provide the missing bridge between the quantum world and the realm of spacetime curvature. In this light, the quest to understand a magnet lifting a paperclip becomes synonymous with the search for the holy grail of theoretical physics, a single, coherent theory of everything. The faintest force is pointing us toward the grandest possible unification. The equations of Kaluza-Klein, the vibrating strings of M-theory, these are languages of profound abstraction. Yet their core idea that reality holds secret folds has escaped the confines of academic journals and ignited the global imagination. It resonates because it speaks to a deep, almost primal curiosity. What if there is more than meets the eye? This question has become fertile ground for storytellers, transforming dense theoretical physics into narratives of wonder and adventure. Science fiction has long been a partner in this exploration, taking the seed of scientific speculation and growing it into vivid, emotional journeys. A novel like Madeleine Ellingel's A Wrinkle in Time gave us the Tesseract, a fold in the fabric of space allowing instantaneous travel, a concept that beautifully simplifies the geometric heart of wormholes and extra-dimensional shortcuts. Decades later, films like Interstellar brought the visual poetry of higher dimensional geometry to the big screen, depicting a universe where love and gravity could transcend time, all framed within the hard science of a rotating black hole and its multidimensional implications. These stories do not present accurate blueprints of string theory. Instead, they translate the feeling of the science, the awe and mystery of confronting a reality vastly stranger than it appears. They ask the audience to feel the disorientation and the possibility. When a character steps through a portal into another realm or perceives time as a physical dimension they can navigate, it is more than entertainment. It is an experiential analogy for the physicist's intellectual leap. This cultural conversation does something essential. It builds a bridge. The staggering weakness of gravity, a puzzle confined to chalkboards and collider data, becomes connected to a shared sense of wonder. A viewer who is captivated by the imagery of Interstellar might later encounter a documentary on the hierarchy problem and feel a spark of recognition. That abstract quest for hidden dimensions is no longer distant. It is the real-world counterpart to the cinematic mystery that moved them. This creates a powerful feedback loop. Public fascination fuels support for fundamental research, for building the next great observatory or particle detector. It inspires a new generation to look at the night sky not as a ceiling, but as a window, wondering what architecture lies behind the glass. The cultural impact reshapes our collective story about the universe. For centuries, the dominant narrative was one of discovery and conquest, mapping a static, clockwork cosmos. The idea of hidden dimensions introduces a narrative of unfolding mystery. Our universe is not a solved puzzle, but a living text with pages we are only learning how to turn. It suggests that the greatest discoveries are not just about finding new things in space, but about discovering new kinds of space itself. This transforms our place in the cosmos from central observers in a finished theater to explorers in an endless mansion, aware that most of the doors remain locked, their contents unknown. That shift is profoundly humbling and infinitely exciting. It means the questions of theoretical physics about why gravity is weak or how many dimensions exist are not academic exercises. They are part of humanity's ongoing effort to read our cosmic context, to understand the stage upon which all of our stories, all of our art, all of our lives are performed. The search for hidden dimensions, then, becomes more than a scientific pursuit. It is a cultural act, a testament to our refusal to accept the surface of things, and our enduring hope that the universe holds deeper layers of beauty waiting to be revealed. The mystery of gravity's weakness is a bridge connecting distant islands of human thought. To truly grasp the idea of hidden dimensions, physicists cannot work alone. They must collaborate with mathematicians who speak the language of shape, with philosophers who question the nature of reality itself, and even with theorists who study the flow of information. This pursuit transforms a physics problem into a vibrant crossroads of interdisciplinary insight. At the heart of string theory lies a profound mathematical object, the Kaluza-Klein manifold. This is not a simple shape like a sphere or a donut. It is a complex, multi-dimensional form, a specific kind of geometric space that exists in 6 dimensions, curled up at every point in our universe. Visualizing it is nearly impossible for our 3-dimensional minds, but its properties are precisely calculated. The exact way these manifolds are folded determines the number of particle generations, the forces we feel, and the very constants of nature in our cosmic slice. Developing the mathematics to describe these shapes has pushed the field of geometry into entirely new territories, creating tools and concepts that mathematicians would have explored for their own abstract beauty, regardless of any connection to physics. Here, the quest for a physical answer drives pure mathematical discovery. Simultaneously, this work forces a deep philosophical reckoning. If the true nature of reality involves dimensions and geometries we can never directly perceive, only infer through mathematics and indirect experiment, what does that say about scientific realism? This is the philosophical view that the world described by science is the real world, independent of our minds. The hidden dimensions proposal tests this to its limit. We are asked to believe in the physical reality of objects Kaluza-Klein manifolds, multidimensional branes that are, by their very definition, permanently beyond any form of direct empirical access. Our evidence would always be secondary, a pattern in particle collisions or a subtle deviation in gravity's pull. This elevates the role of mathematical elegance and consistency as guides to truth, a principle that makes some empiricist philosophers deeply uneasy. It sparks debates about whether we are discovering the universe's architecture or constructing an immensely sophisticated mathematical story that simply organizes our observations. Even concepts from information theory, the study of how data is encoded and transmitted, begin to weave into this tapestry. Some researchers suggest that the fundamental laws of physics, perhaps even space-time and gravity themselves, might emerge from underlying principles of information processing, a concept with echoes in the way holograms encode three-dimensional images on two-dimensional surfaces. This confluence of disciplines is not a side effect. It is a hallmark of fundamental research at the very edge of understanding. A single, stubborn clue from nature, the incredible feebleness of gravity, becomes a catalyst. It forces mathematicians to invent new languages of shape. It compels philosophers to refine ancient questions about knowledge and reality. It invites computer scientists and logicians to consider the universe as a system of computation. The pursuit does not merely seek an answer to a physics problem. It becomes an engine for expanding the entire frontier of human knowledge, demonstrating that our deepest questions about the cosmos cannot be contained within a single field of study. They ripple outward, challenging and enriching everything they touch. The quest to hear gravity's faintest whispers is building toward a symphony of new instruments. While today's experiments listen in quiet rooms or smash protons underground, the next generation of probes will venture into the pristine silence of space and push the boundaries of the infinitesimally small. These are not mere upgrades, they are entirely new sensors designed to catch the subtlest signatures of hidden dimensions or new forces that our current tools might miss. Leading this cosmic orchestra is a mission called LISA, the Laser Interferometer Space Antenna. Imagine 3 spacecraft flying in a perfect triangular formation millions of miles apart, connected only by beams of laser light. They will form the largest and most sensitive scientific instrument ever built, a gravitational wave observatory free from the seismic rumble of Earth. LISA will listen for ripples from events far more ancient and massive than any ground-based detector can hear, like the slow, spiraling dance of supermassive black holes at the hearts of merging galaxies. In the exquisite quiet of space, it could detect deviations in how these waves travel, tiny shifts in their timing or polarization that might hint they have brushed against the geometry of extra dimensions on their billion-year journey to us. This would turn gravitational waves from messengers of cataclysm into probes of the universe's hidden architecture. Closer to home, the unique environment of the International Space Station offers a pristine laboratory for testing gravity's most fundamental laws. In microgravity, the constant, overwhelming pull of Earth is reduced to a whisper, allowing scientists to perform experiments of impossible delicacy. One such project involves testing the equivalence principle, the idea that all objects fall at the same rate regardless of their mass or composition, with unprecedented precision. By comparing the free fall of different test masses in a satellite orbiting Earth, researchers can search for violations so slight they would be utterly drowned out by our planet's gravity on the ground. Finding even a minuscule violation would be revolutionary, a direct challenge to Einstein's framework and a potential signal of new forces or interactions that differentiate between materials, a clue that could point toward a deeper theory. Meanwhile, back on Earth, the frontier of the very small is being pushed not with immense energy, but with exquisite control. Next-generation tabletop experiments are using clouds of atoms cooled to near absolute zero, held in place by lasers, to measure gravity's pull at microscopic distances. These cold atom experiments can sense forces a billion times smaller than the weight of a single cell. Other efforts employ nanotechnology, crafting tiny, vibrating cantilevers or oscillators to feel for any change in gravity's strength when two minuscule masses are brought within a hair's width of each other. These are the quietest, most precise measurements of force ever attempted, hunting for the moment gravity's behavior changes as it runs out of room to escape into a hidden dimension. On the high-energy frontier, plans are already being drawn for the successor to the Large Hadron Collider. Future circular colliders with circumferences potentially spanning 100 kilometers or more would smash particles together at energies many times greater than today's record. This would open a window to phenomena completely inaccessible now, allowing us to search for the superparticles predicted by supersymmetry, or to produce and study the Higgs boson with such detail that even the most subtle anomalies in its behavior would stand out. It is in these extreme, recreated moments of primordial energy that we might finally see direct evidence of strings vibrating, or witness the telltale missing energy of a graviton slipping into the bulk. Each of these avenues, the silent listening of Lisa, the delicate free fall in orbit, the quantum chill of tabletop sensors, and the furious collisions of future colliders, represents a different strategy in the same grand campaign. They show that the mystery of gravity's weakness is not a static puzzle awaiting a single eureka, a moment, but a dynamic, multi-front investigation. The coming decades promise not just more data, but entirely new kinds of data, each capable of revealing a different facet of the truth. This ongoing pursuit ensures the field remains vibrantly hopeful, driven by the conviction that the faintest force in our universe is still our best guide to its deepest secrets. Is the weakness of gravity a clue to the universe's design, or simply a condition of our own existence? This question sits at the heart of a fierce and fascinating debate that divides some of the brightest minds in physics. On one side, proponents of anthropic reasoning argue that the answer is staring us in the face. We should not be surprised to find ourselves in a universe where gravity is weak, because only in such a universe could stars burn for billions of years, planets form, and complex life like us ever arise. In a cosmos where gravity was even slightly stronger, stellar furnaces would rage and flicker out too quickly for the slow, delicate chemistry of life to ever begin. From this perspective, the staggering gap between the forces is not a puzzle to be solved by a single equation, but a cosmic prerequisite for observers. Theoretical physicist Leonard Susskind, a leading voice for this view, frames it within the vast landscape of string theory. With a near infinite number of possible universes, each with different physical constants, it is statistically inevitable that some will have the right numbers for life. We quite simply live in one of those habitable pockets. The explanation is not in the laws, but in the selection effect of our own consciousness. For supporters, this is a profound and legitimate scientific insight, using probability and the observed fact of our existence to narrow down the possible theories of everything. It shifts the goal from finding a unique, inevitable set of laws to understanding the distribution of possibilities within a multiverse. Yet, to many other physicists and philosophers, this line of reasoning feels deeply unsatisfying, even unscientific. The criticism is sharp. They argue that invoking our existence to explain a fundamental constant is a form of circular reasoning, a philosophical surrender that halts further investigation. It replaces a dynamical, mechanical explanation, a story of cause and effect written into the equations of the universe, with what they see as a tautology. We exist because the constants allow it, and the constants are what they are because we exist. Critics demand more. They want to know the engine, the specific mechanism within the laws of physics that actively sets gravity's strength to this precise, tiny value. They seek a process, a symmetry-breaking event, or a geometric stabilization that actively enforces this hierarchy, something that would be true even if no one were here to notice it. To them, anthropic reasoning risks making physics untestable. retreating into a realm of metaphysical speculation about unseen universes we can never access. This debate is about more than gravity. It strikes at the very definition of a scientific explanation. What kind of answer will truly satisfy our curiosity? Is it enough to know that our universe is one possibility among many in a grand cosmic lottery, and we hold the winning ticket? Or does the human drive to understand demand a deeper story, one that reveals a necessary elegance woven into the fabric of reality itself? The quiet tug you feel holding you to the earth is now a mirror, reflecting our deepest questions about knowledge, existence, and what it means to truly explain the world. The dream of unification is woven into the very fabric of science. It began not with subatomic particles, but with an apple falling from a tree. Isaac Newton looked at that apple and saw the same force that held the moon in orbit around our planet, uniting the heavens and the earth under a single law of universal gravitation. It was a monumental leap, the first great synthesis. Centuries later, James Clerk Maxwell performed another act of unification. He showed that electricity and magnetism, once thought to be separate phenomena, were two faces of a single, elegant force, electromagnetism, described by a concise set of equations that also predicted the nature of light itself. With these two pillars standing tall, physics seemed to be building toward a complete picture. Then came Albert Einstein. His theory of general relativity reimagined gravity not as a force, but as the curvature of space-time, a geometric masterpiece. Yet, he spent the latter half of his life haunted by a vision he could not realize, the dream of a unified field theory. He sought to weave gravity and electromagnetism into a single geometric tapestry, to find one set of equations from which all of reality would flow. He ultimately could not bridge the divide, and the quest passed to a new generation. That dream has now evolved, but the central challenge remains strikingly familiar. Today, we have the Standard Model, a breathtakingly successful theory that unifies electromagnetism with the strong and weak nuclear forces. It is a quantum theory of almost everything, except for one glaring omission. Gravity once again stands apart. Its profound weakness is not just a curious detail. It is the final, stubborn barrier in this century's long quest for a grand synthesis. The search for hidden dimensions, for the geometry of strings and branes, is not a departure from this historical arc. It is the latest, most ambitious chapter in the very same story. It is the current expression of humanity's relentless drive to find a single, coherent, and elegant set of principles that govern the cosmos from the smallest quark to the largest galaxy cluster. This pursuit has always been about more than just cataloging nature's parts. It is about understanding the connections between them, revealing a deeper harmony. Each step in this journey, from Newton to Maxwell to Einstein to the theorists of today, has reshaped our conception of reality. Even when a theory is incomplete or later refined, the act of striving for unification forces us to ask better questions, to develop new mathematics, and to see the world in radically new ways. The current focus on extra dimensions, driven by the puzzle of gravity's feebleness, continues this noble tradition. It pushes the boundaries of geometry and asks us to conceive of a reality far richer than our senses report. The value of this quest may not lie solely in a final, triumphant equation. It lives in the process itself, in the way this profound mystery drives innovation, deepens our understanding, and continually reminds us that the universe is a place of hidden connections waiting to be discovered. The story of physics is the story of finding unity in apparent diversity, and the faintest force of all is now our most compelling guide. The faintest pull in the universe has become our most trusted guide. This journey has taken us from a magnet lifting a paperclip to the edge of hidden dimensions, revealing that gravity's profound weakness is not a flaw in nature's design. It is a carefully inscribed clue, a luminous signal pointing toward a deeper layer of reality. For the theorist sketching equations late into the night, this staggering gap in strength is a compass needle. It steers their mathematics away from dead ends in four-dimensional space and toward the richer geometries of strings and branes. The numbers themselves demand more room, whispering that the true stage for physics must be larger than the three dimensions we perceive. That apparent feebleness is the key mathematical constraint, shaping models of curled-up Calobi-Yau manifolds or vast, warped bulk dimensions. Without this glaring puzzle, the drive to imagine such extraordinary architectures would lack its most compelling evidence. For the experimentalist calibrating a laser or sifting through petabytes of collision data, the weakness is a detailed map. It tells them precisely where and how to look. It dictates building instruments sensitive enough to measure forces smaller than a single cell's weight, probing the submillimeter world where gravity might finally change its behavior. It defines the signature they hunt for in particle detectors, that telltale missing energy which could mark the moment a graviton slips into the unseen bulk. These two paths, one of abstract geometry and one of meticulous measurement, are both navigated by the same beacon, gravity's quiet voice. This synthesis leads to a transformative perspective. What we experience as the universe's weakest force may be a profound illusion of confinement. We are like deep-sea creatures who have only ever known the immense, crushing pressure of the ocean depths. To us, that pressure is the constant, overwhelming condition of reality. We could not conceive that just a short journey upward, a direction we cannot easily travel, lies a realm of gentle atmosphere and boundless space where the concept of such pressure is almost meaningless. Our experience is true, but it is not the whole truth. In the same way, gravity's feebleness in our three-dimensional slice may be a local condition, not a universal law. Its true strength could be echoing in rooms we cannot enter, diluted by its freedom to travel through the full, hidden geometry of the cosmos. This means the signal we have been decoding is not one of limitation, but of liberation. It suggests that our reality is far more expansive, intricate, and interconnected than our daily senses could ever suggest. The very characteristic that made gravity seem like an afterthought in the cosmic play is now its most distinguishing and important feature. It is the thread that, when pulled, begins to unravel not just its own mystery, but potentially the unified fabric of all existence. In the end, the greatest paradox may be this, that in the universe's softest whisper, we find the clearest instructions for uncovering its loudest truths. That gentle pull holding you to the earth is a message from the hidden architecture of the cosmos. We have traced a single, astonishing clue: gravity's profound weakness, across a landscape of ideas, from the stark mathematics of the hierarchy problem to the mind-bending possibilities of curled-up dimensions and cosmic membranes. This journey reveals that the faintest force is not an anomaly to be ignored, but a luminous signpost. It points insistently toward a deeper, more unified reality, one where the rules are written not just in particles, but in the very geometry of space itself. The numbers are a constant, quiet demand for a bigger stage. Physicist John Archibald Wheeler beautifully captured one half of the cosmic dialogue when he said, "Spacetime tells matter how to move, matter tells spacetime how to curve." Our exploration suggests a thrilling next line for that conversation. Perhaps hidden dimensions tell gravity why it is so gentle. This is the profound takeaway. The universe's greatest puzzles are not dead ends. They are invitations. The staggering weakness you experience every single day, the reason a tiny magnet can defy a planet, is an open question written into the fabric of existence. It reminds us that our cosmos is still a place of magnificent, unfolding mystery. We are not merely inhabitants of a finished stage. We are explorers in an endless mansion, learning that the faintest whisper in one room can echo the grand design of the entire structure. If this journey through the hidden folds of reality sparked your curiosity, there are countless other enigmas waiting. We would love for you to join us as we continue exploring space's greatest questions. Let us know in the comments below, does the idea of extra dimensions reshape how you see our place in the cosmos? Your perspective is part of the ongoing discovery.